Okay. So yesterday we were running this script x2 biped.py, which was making this biped robot follow a sinusoidal trajectory with the center of mass. And I think we stopped right after the first execution, where we just verified that the thing worked. But I think before moving on, I would like to play a bit with the script. So for instance, if you look at the slides, they suggest you to change the gains of the COM and the posture task, change the weights, try to set the reference COM outside the support polygon. So the support polygon is the convex hull of the feet. So if you try to make the COM move outside, basically the support polygon, what happens? And try to increase the frequency of the COM sinusoid, and try to add a contact on the hand. So maybe we're not gonna do everything, but at least I would like to try out a couple of these things. So let me open that script again. Mi scusi, non riesco a sentirla. Ok.
Ora sì, la sento.
Ok. Ti puoi far vedere un attimo, Giulia, così verifico che sei tu?
Buongiorno.
Okay, so this was the script. X2 biped. And there was also a configuration file, which is called talosconf. So here we have the weights of the task, which we can change here. And we have also the gains. So at the moment, well, let's run. I've already run the script, but it doesn't plot anything. That's a bit surprising. Maybe there is a flag we need to enable to show the plots. Maybe it did plot something, but I closed it. It should plot something. It's working. Yeah, it did plot something. I closed it without realizing. Okay, so we can see the tracking of the COM. So this is just CM0, CM1, CM2. Okay, so this is XYZ of the CM position. Well, the sinusoid is only in the y direction. So basically what we are seeing in the X and Z are really minuscule movements. If you look at the scale, you can see that it's less than 1 millimeter. And in the y direction, the tracking is pretty good. It doesn't start perfect in the beginning, but that's reasonable because the robot starts with 0 velocity. So of course also the COM has 0 velocity. And the reference instead has a non-zero velocity. And that's the problem when you try to track a sinusoid, that you start with a non-zero velocity. So in the beginning, you can expect a bit of tracking error, but in half a period, you're already on the reference. So that's pretty good. And the same happens if you look at the velocities of the COM. And here we look at the acceleration. So everything is working quite fine. So we can try to make things not work fine. So for instance, one thing we could do is to lower the weight of the COM task. Now it is 10. We can set it to 1 and see what happens. And what we should expect is that now the postural task is more important, and so we're going to have a lower quality tracking. Probably this was already the starting point yesterday, now that I think about it. So we already did the first point of changing the weight, but yeah, doesn't hurt to do it one more time. Yeah. So this we already saw, but what we can do now is, starting from this weight, we can, instead of increasing the weight, we can increase the gain. Because it's not, I think, especially in the beginning, it's not very clear what's the difference between the weight of the task and the gain of the task, because they have different roles, but sometimes you can solve a tracking problem by increasing the gain, and other times you can solve it by increasing the weight. So we can check whether in this case, by keeping the weight small, so 1, and just increasing the gain,
the gain of the center of mass.
Yeah. Right. So let's check if just by increasing the gain, but without modifying the weight, we see an improvement in the tracking of the COM. What is your guess? You think it's going to improve or not? I think it's going to improve a little bit, but maybe not as much as increasing the weight. A joke? Yeah. Okay, I was actually wrong. It improves even more than increasing the weight. And this is not really trivial to predict what's going to be the effects of either increasing the weight or increasing the gain. So increasing the gain, what is it going to do? We can see it, I think, quite clearly in the acceleration plot. Increasing the gain, basically for the same tracking error, is going to ask you a higher acceleration for that particular task. So in this case, the COM. So we're asking much higher accelerations now than before, well, 10 times higher for the same tracking error. And then that error there between the real acceleration and the desired acceleration is going to be minimized, but together with the other errors for the other tasks, such as the postural task. And which one is minimized more depends on the weight. Okay, so the weights are the ones that basically settle the conflicts between the task. So in case of conflict, and here there is always a conflict because the postural task takes all the degrees of freedom of the robot. So whatever you do is going to be in conflict with the postural task, basically. And the postural task asks you to not to move. So whenever you have a task that requires some motion, it's going to be in conflict with the postural task. So we're going to have a conflict between postural task and CUM task, and how much you move in one direction or the other, so satisfying one task or the other, depends on the weight. So in this case, the effect of increasing the gain or increasing the weight is quite similar, because by asking for a higher acceleration, you're making the acceleration error on the CUM larger, which means that in relative terms, with respect to the acceleration error in the posture task, it's going to weigh more. So it's similar to increasing the weight, but it's not exactly the same. Okay. So the weight only have an effect if you have a conflict between the tasks, whereas the gain has always an effect, because you're really asking basically the tasks to converge faster.
Can you go back to the plots for the tracking the position? 1 second.
I think it's this one.
Because it looks like there is kind of a delay in the tracking of the second component with respect to the previous case.
I think we had this delay even before. Yeah, I mean, we can try to rerun it. It's pretty fast. It's true that there is some delay. We can try to quantify it by zooming in a little bit. So it's almost 2 grid steps. So that's 0.4 seconds, so 40 milliseconds. We can check if we had that even before. So before we had this smaller, KPCOM was 10, but we had this bigger. Let's see if we have still this 40 milliseconds of delay. It's also possible that the delay is larger when we have higher gains, and I can explain you why in a second. Let me first check if that's the case. Let's try to zoom in here. This is 1, 2, 3, 4, 5 steps. Each step is 2 milliseconds. So we have 10 milliseconds compared to before, which was 40. So yeah, here's a delay. I mean, increasing the gains, we have a larger delay, which makes kind of sense, because when we have a very high feedback gain, it means that the feed forward component, so the reference acceleration, is smaller relative to the feedback part of the control, which is the PD part. And it's the feed forward that kills the delay, because if you're working in feedback, by construction, you're gonna be delayed with respect to the reference, because you're only working after you see an error, you're able to act to correct it. And so having a higher gain, it means that the feed forward is smaller in relative terms, So it kind of makes sense that basically you're able to keep up with the reference thanks to the feedback, and that introduces a delay in the system. So yeah, it's a good observation. I didn't notice. So I would say that in general, if you're able to make things work by using not too high feedback gains, it's better, especially on a real platform, because high feedback gains can be very problematic in practice. So they introduce delays, they amplify noise. If you have sensor noise in your encoders or your velocity estimates, and you have high feedback gains, then the noise is amplified. So they can introduce vibrations in the system. That doesn't happen in a perfect simulation like this, but in a real robot it would. And they make the system stiffer. So it's more dangerous to interact with the robot physically, because then the robot is going to react in a very stiff way. So it can generate high contact forces in case something unexpected happen. So a robot with low feedback gain is a safer robot. Okay. So ideally, you want to try to keep the feedback gains as small as possible. But it's hard in practice because you need a very good model in order to have low feedback gains, because you're relying more on the feed-forward component. So in this case, I would say that the ideal setting is just this one with a higher weight on the center of mass, which works well and doesn't have the delay. Okay, so we can try another thing, which is increasing the amplitude of the sinusoid we are tracking. So that's defined here. Right now is 5 centimeters. We can try to make it 20 centimeters and see what happens. I'm not sure if 20 is already outside the support polygon, but probably it is. Yeah, it is. Bam. So the thing stopped because the QP problem could not be solved. That's the error we're getting. There is also an error in the plots. Yeah, this comes from matplotlib. So probably we are asking matplotlib to plot things, to plot values that are too large, and so this doesn't work. And we can also see it from the graph that they're really terrible. I mean, the scale here is 10 to the 307, so we cannot even try to zoom in because it would take forever. So I think we should instead, okay, the acceleration plot looks better. I wonder why that's the case, because accelerations should be even higher. I have a guess. Let me check. Yeah, okay. I think we should here multiply everything times not a number, because I'm creating this all these matrices with the empty method. So empty gives you memory without initializing it. So inside that memory, you could have whatever junk there was there before. So it's a good practice instead to pre-multiply everything times not a number, because when you plot not a numbers, they don't show up in the plot. So that's a better initialization for that memory. Python was complaining whether I was doing this multiplication times not a number. That's why I removed it a couple of days ago, but in hindsight, I think it's better to keep it. So you can see that the robot moves to the right, but then it's not able to come back to the left. Okay, so now the plots are nice. So the problem comes from the y direction. So the second plot, we start moving to track this reference, but then, I mean, we don't even reach the 20 centimeters that we asked for. Starting on this point, the robot should go back, but it's not able to do so. It keeps going to the side and until it diverges. So this divergence is going to be a key property of the model we're going to talk about in the next slide, which is a linear inverted pendulum model, which really captures this divergence of the center of mass of a biped robot. And the divergence comes from the fact that we are not able to deliver the acceleration that we are asking for. So the reference acceleration is the red one, but that's just basically a sinusoid. The desired acceleration is the green one. And we can see that in the beginning here, maybe we can zoom in a little bit. Well, in the very beginning, we are not able to provide the desired acceleration. We are saturating here. So we are asking the center of mass to accelerate too much, even in the beginning, and it's not able to do so. Again, this limitation will become clear when we introduce the linear inverted pendulum model. Then, when the desired acceleration becomes lower, right here, we are about at 1.8 meter per second square. We can see that the tracking becomes good. So the blue and the green are more or less matching. They're not exactly matching because we have also the other tasks, such as the postural task, but they're roughly matching. And they keep matching until this point. And then what happens at this point is that the desired acceleration keeps increasing, but we cannot do that. So the real acceleration it remains negative, but not as much as we would like. And this is what causes the divergence of the center of mass, because we are not able to decelerate as fast as we would like. So we can see that here, the desired acceleration keeps becoming more and more negative because we're asking it to stop, to decelerate, but the system is not able to decelerate as fast as we are asking it to do. And actually, after a little while, not only we are not able to decelerate as much as we would like, but we start accelerating. So the desired is negative, but the real one is positive. So we are pushing in the opposite direction of what we are asking the system to do. But that's normal because basically we are asking the robot to do something that it cannot do. I mean, nobody can do that. You cannot move your center of mass basically beyond your foot to the sides and then come back without moving your feet. You just fall down because of gravity. So this should highlight the importance of having a reference center of mass trajectory, which is compatible with the limitations of the robot, which is going to be the main subject of the next hours together. Another thing that is quite, I think, entertaining is to increase the frequency. So we go back to a reasonable amplitude, to the 5 centimeters we had before, but we increase the frequency. So now the frequency is 0.5, we can make it, I don't know, 5 and see what happens. Of course, 5 is way too high. So I don't think it's going to be able to track. If you're lucky, it doesn't fall down. I'm not sure we're going to be lucky. Yeah. I think even in this case, it's interesting to look at the acceleration plot. And we can see the reference and the desired acceleration, they are very large. We're asking for a value of 50. But the system is able to deliver a value probably around 2 or 3. Yeah, here we are at 3.7. That's the maximum it can deliver. So we can clearly see that there is a limitation in how much we can accelerate our center of mass. This is in the lateral direction, but it would be the same in the forward direction. We have the same limitation. And this limitation comes from the fact that our feet have a finite dimension. So when you push to the left, basically what you're doing is that you're pushing with your right foot. You're stamping on the ground with your right foot. And the more to the side your right foot is, the more you're pushing. But in this case, your foot is fixed on the ground in a certain position, so you can only push so much. So we have this limitation, and even if we ask for a much higher CM acceleration, we are not going to get it. And the result is that, well, the acceleration tracking is very poor, and that results in a CUM trajectory that diverges to the side. Whether we diverge or not, in this case, is hardly predictable. Probably if we ask for something intermediate, like maybe 2, even if we are not able to track properly, we may not diverge. Let's see. Doesn't look good. Okay, so even 2 is too much. Maybe 1 is going to work. I'm just curious at this point, so I want to know. It's bending. Yeah, I don't know how long it's gonna last. But maybe enough to finish the simulation, yeah. Okay, so we can see that it wouldn't last much longer because it's slowly diverging, but slowly enough that it doesn't fall down in 5 seconds.
Why does it diverge? I mean, the reference trajectory oscillates around the middle point, so I would expect like the road to move around in place and not diverge.
I think there is a bias coming from the fact that we start moving in one direction rather than in the other, and that makes the trajectory skewed in one direction. Yeah, it's hard to predict why that's the case. But yeah, it comes from the fact that the initial desired acceleration is not 0, is a positive value. And so, yeah, we get this slow divergence to one side. I think this should be even possible to reproduce and predict by using the simplified model we're going to introduce next. And here we can clearly see again this saturation of the COM acceleration. We can see that really the system cannot produce more than a certain value. And we're going to understand where this limitation comes from in a moment. Okay. So there is one thing left, which is adding a contact on the hand. But for the sake of time, I think I'm going to skip that. It takes a while. We will need to modify the code. I suggest you do it to gain some experience with this library later. There is also another script which we can just quickly run so that you know it exists. It's X3 biped balance with GUI. This is just for fun. So I've created this simple GUI. That you can use to play with the robot. So you have the robot there, and with this GUI, you can move the reference of the center of mass, and the robot reacts. And actually, if you click this, I don't know if it works. No, it doesn't. You don't click that. So we can move the reference. You can see the reference is represented by this red ball. And you can see how the robot reacts. And you can even, if you move the center of mass once to the side. So for instance, now I moved it to on the right foot. So I can break the contact on the left foot. I can make the left foot rise. You can see it's no longer on the ground. And now I can make it move forward. And then back on the ground. Again, the reference is this purple ball. And then I can re-establish the contact with the left foot by clicking this on this button. And then I can, if I'm really patient, I can move the COM position forward and on the right foot. No. I think I didn't click this well. So I didn't really make the contact with the left foot again, so it fell down. But I mean, I think you get the idea. You can make the robot walk by making breaking contacts, moving the center of mass and the feet references. You can play a bit with it, and you can see how difficult it is to do that by hand, which motivates us to look further and try to develop an automatic method for doing this planning of center of mass and feet trajectories that allows the robot to walk effectively. And you also, yeah, we can also quickly rerun this. There is also another thing that you can play with, which is pushing the robot and see how it reacts. So here you can specify a velocity that you want to instantaneously assign to the center of mass not assign, is add. This is a velocity that you add. So for instance, you can try to add a velocity of 0.1 meter per second in the forward direction and see what happens. So you click this. Okay, 0.1 is very small, so I can make it bigger. 0.2, okay, now you saw it. It started moving forward. But it's able to sustain that. We can try to make it bigger, I don't know, 0.3. That was too large. We pushed it too much. And you can do that also in the lateral direction and in the vertical direction if you want to see how it reacts. Okay. Any question? Let's move on then. So the next subject, which is the second part of this course, is trajectory optimization for walking. So basically the motivation for this is what we just saw. For making the robot walk, we need a reference trajectory for the center of mass and the feet. And we just saw that it's quite difficult to provide a reasonable reference trajectory that makes the system really work, because the robot is not able to just track any center of mass trajectory because it has a limit, a bounded support polygon. And so as soon as the center of mass basically is outside the support polygon, the robot is gonna fall down. So how can we compute these reference trajectories? So the reason why TSID is not enough to make the robot walk, or actually to make the robot do also other stuff, but walking is a very good example, is that TSID has no notion of the future state. So we are just working in TSID, looking at the current positions, velocities, and accelerations, and that's it. So we have some reference accelerations, and we try to make the real accelerations of the robot as close as possible to these reference accelerations, which represent different tasks such as center of mass, feet, posture, angular momentum, and so on and so forth. So for this kind of control framework, it's very hard to anticipate future constraint violations. And we already touched on this subject when we discussed the problem of joint position constraints or obstacle avoidance constraints. And the example I typically do in this context is, imagine you have a car. Look how beautiful my car is, which is going towards a wall. So this is the wall. And if you look at things in the way TSID does, you're just going to look at what happens at the next time step, which for TSID is something like a couple of milliseconds. And if you do that at the next time step, well, everything is fine, everything is fine, everything is fine, everything is fine, everything is fine. Until here, everything is fine, because if you only look at the next time step, at the next time step, you're not colliding with the wall. So you're only going to realize there is a problem when you're sufficiently close to the wall that you can see the collision in the next time step. But that means that you're 2 milliseconds away from colliding. And at that point, whatever you do, it's too late. Because at this point, if I am at a couple of centimeters of distance from the wall and I'm running at 50 kilometers per hour, there is no way my brakes are sufficiently strong to stop me. And so at that point, I'm gonna hit the wall no matter what I do. And with TSID, you have this problem, and it's very hard to work around it. So if you wanna use a tool that doesn't have this problem, that solves this problem, that tool is trajectory optimization. Because with trajectory optimization, we are not only looking at what happens in these very moments, but we are looking at the future evolution of the system, because we are optimizing a trajectory. And so we can make sure that the whole trajectory does not collide with the wall, does not violate constraints. And so everything is going to be fine, not only in 2 milliseconds, but maybe in 10 seconds or something like that. We have a horizon, a prediction horizon. The problem, of course, with trajectory optimization, if you have any experience with that, is that it's much more computationally expensive. So it becomes hard to do that in real time if you have a complex robot such as a humanoid, where you have many degrees of freedom. And so the number of optimization variables of your problem explodes. So a good compromise solution, which is the one we're going to adopt in this course, is to use trajectory optimization for planning a reference motion. And then we're going to use TSID for tracking that reference motion. Because in this way, we use trajectory optimization offline, so we don't care if it takes a long time, because we just have to do it once and not while the robot is controlled. And then we can use TSID online, which is very fast to track that reference motion. So we use each tool in a domain where it shines. So let's talk about trajectory optimization for doing locomotion. And actually what I'm going to say applies also to manipulation, because these two problems, they share many common features. And the bad news is that this is a really hard thing to do, even if you want to do it offline. And the reason why it's hard is that you have contacts with environments that are constantly being made and broken. And this is common for both locomotion and manipulation. So in locomotion, you make contact typically with your feet on the ground, and you break this contact every time you move your foot off the ground. And look, in manipulation, it's the same. If you want to manipulate an object, you need to make contact with your fingertips. But then typically to do some fine manipulation, these contacts are broken and made several times through the motion. So making and breaking contacts is very difficult, because these contacts are typically rigid, because the ground is rigid and objects are most of the times rigid. So these are very well modeled using a hybrid dynamical system formulation, because every time you make a contact, you're basically adding constraints on your motion. That is something that we saw when discussing TSID, because you can no longer move the point of your robot that is in contact, because you cannot penetrate a rigid object by definition of rigid object. So you have these contacts that are added and removed from your dynamics. So your dynamics is changing instantaneously in a non-smooth way. So you need a hybrid system formulation. Do you know what a hybrid system is? Well, you know. Do you know?
Yes.
Okay. Julia, at home, do you know what a hybrid system is?
Actually, no.
No, okay. No big deal. A hybrid system is a system that is described by a set of differential equation of this kind and a set of discrete time equation of this kind. And you apply either one or the other depending on the state. So if X belongs to, what's the typical symbol used?
C, like the G.
Ah, okay, C. So you set C, or here if the set belongs to another set, D. So you have two sets, and depending on whether the state is in one set or the other, you use the differential equation, which has is characterized by a smooth evolution of the state in time, or you use the discrete time evolution, so the GMAP, which is characterized by often jumps in state space. So this makes the system state trajectory non-smooth and non-differentiable. So you cannot apply a classic numerical optimization technique, and you need to rely on non-smooth optimization approaches, which are much harder to work. They are more computationally expensive, and yeah, very few people try to do that because it's a hard problem. So that's option number one, which is not really an option in practice. Option number two would be to say, well, yeah, these contacts are hard, but we could approximate it using a soft contact model for which we tune the stiffness of the contact to be quite high. And that is a very good approximation of a really rigid contact. And that would be true. You can approximate a rigid contact using like maybe a spring damper contact model, saying that the contact force that you get is proportional to how much you're penetrating inside the object. And if you tune this spring, basically the stiffness of the contact model to a very large value, such as 10 to the power of 5, something like that. If you do your simulation in that way, well, the behavior you're going to see is going to be very similar at your naked eye to the simulation with a perfectly stiff contact model. So that would be a reasonable approximation. The problem is that since you need to use a very high value for the contact stiffness, what you're going to get is a stiff differential equation. So now the system is described by a differential equation, something like that, which is smooth. Smooth meaning that it can be differentiated. You have a derivative that is defined everywhere, but the derivatives basically get so large that to numerically integrate this differential equation and get a reasonable result, you need to use a time step for your numerical integration scheme that is very small. Okay. So maybe you need to integrate with a time step that is 10 to the minus 5 or 10 to the minus 6. You can think of it as roughly inversely proportional to the stiffness that you're using for the contact. It's not an exact relationship, but roughly speaking, that's how it works. So that's going to result in a very slow computation. So again, it's not something that works well in practice. It's similar to the conclusion we got when talking about rigid contacts. So what people ended up doing is something that is neither one nor two, which is, let's assume that the contacts are rigid, but instead of trying to figure out which contacts I should make or break, I'm going to pre-assign the contact sequence by hand. And if you think about bipedal locomotion, that makes a lot of sense because we know exactly the sequence in which contacts are going to be made in bipedal locomotion. We're going to make a step with the right foot, breaks the contact on the left foot, then make a step with the left foot, breaks the contact with the right foot, and so on and so forth. We repeat this cycle forever when we are doing bipedal locomotion. If you have a quadruped, you have many more options, of course, because you have 4 feet, but you can predefine the gait of the quadruped. You can decide, I'm going to do a trot. And once you decide you're going to trot, then you know exactly the sequence in which you're making and breaking contacts. And if you already know this information, then your system is no longer a hybrid dynamical system. It's just a time-varying dynamical system. So you still have these extra constraints that are going to appear and disappear in your dynamics, but they're no longer based on your state. They're just based on time. Okay. So you're going to have basically different dynamics for different times during the horizon. So in our case, I can make it a bit more specific. Maybe we have two different, well, actually, we could have even three. We could have FL, which is the dynamics if left foot in contact. Then we're going to have x dot equal fr of xu if right foot in contact. And we could also have fd if both feet in contact. So D stands for double support. So you have both feet on the ground. So we have three different dynamics, but instead of switching between one and the other depending on your state, you know exactly the sequence in which you're gonna meet these dynamics. So you know that you're gonna start in double support. So you start with FD, and then after a certain time, you go to FL, then you go to FD again, then you go to F right, and then you repeat. So you have a cycle between these different dynamics, depending on whether you have both feet or just one of them touching the ground. And you know that you switch from one dynamical system to the other when time reaches a certain value. So at T1 you go there, at T2 you go there, at T3 you go there, and then at T4 you go there, and then you keep repeating this time-based cycle. So when you have this kind of dynamical system, well, that's just a time-varying system. So it's no longer a hybrid system. It's no longer non-smooth. So you can apply standard trajectory optimization techniques, even if you have a system with contacts. Of course, by doing that, you lose the ability of automatically discovering which contacts you make and break. So you're giving up on something, but you gain differentiability, and so you gain basically in terms of speed at which you can solve the trajectory optimization problem.
When you talk about smoothness and differentiability, do you mean the f functions to the right-hand side, or also the x, the trajectory of time expected?
So the trajectory could have jumps. So the trajectory itself is not differentiable, but the trajectory optimization problem is differentiable, which is a bit counterintuitive, but that's the case. So we could imagine, maybe to make things a bit simpler, that we don't have jumps even in the states trajectory. So the trajectory is always differentiable, and you can get that just by imposing that at the end of this time. So you know that basically when you're switching from just left foot to double support, you need to have your right foot, which is on the ground and with a zero velocity, to avoid having a jump in the state.
Yeah.
And you can just then impose in the trajectory optimization problem that condition at that specific time. And if you have that, then your state trajectory is going to be continuous.
No, that's fine. Yes. But maybe this will be clear later when we actually look at the equations, because when you make the switch from, for example, FL to FR, you need the two functions to match, otherwise you will have a discontinuity in the derivative of that. So it will not be smooth.
You do have that, but that's not a problem if you already know that you're gonna make the switch. So your trajectory optimization problem remains differentiable, and you can use classic numerical optimization tools. That it becomes a problem if the switch is based on the state. In that case, your system is hybrid. But with this time-based switching, then it's just time varying, and it's not a problem if the dynamics changes. It does change in a smooth way, the dynamics, but the problem is differentiable. Okay, so yeah, it's basically a borderline situation where you're not completely smooth because you can have jumps in the trajectory, but you don't have to deal with the hybrid dynamical system framework, which is way more general and way more difficult for trajectory optimization. And this is where actually lagged locomotion has been hitting hard for years. I mean, as far as I know, all the lagged robots that you can see in videos on YouTube, what they're doing behind inside the codes is something like that. Okay, nobody's doing trajectory optimization with the planning of the contacts embedded inside, because that's way too slow and too difficult. Any question? Okay. So we are now on this new deal that we are going to have fixed contacts, because having optimized contacts is too hard. But even agreeing that the contacts are going to be fixed by the user, the problem is still hard because it's high dimensional. So the humanoid robot we saw, it has something like 40, 50 degrees of freedom. So if you multiply that times the number of time steps of your prediction horizons that you're going to use in trajectory optimization, maybe you have 100 time steps. So you have 40 degrees of freedom times 2 to get also the velocity in the states. You get 80, let's make it 100 for simplifying the computation. I think Siri started for no reason. So 100 times 100, you get 10 to the power of 4. So you have 10,000 variables in your problem. So it starts becoming a quite large problem. You could still try to solve it, but it's large, it's slow, it's non-convex. So it's not something trivial to implement and to make work in practice. So what people have done in my community is to rely on simplified models. So the idea is that if you're able to figure out a model of the system which is lower dimensional and maybe even linear would be ideal, then we could use that to do trajectory optimization super fast and compute reference trajectories for the robot in a matter of milliseconds. And if you're able to do it that fast, actually, we could also do it then in an MPC fashion. So re-executing the trajectory optimization every few milliseconds to update the reference trajectory, not to use a fixed one, which will make the system much more robust to perturbations. And using this mindset, there have been different simplified models that have been proposed for locomotion. One is the inverted pendulum, because the robot, when it's standing on one foot and moving forward, it looks a lot like an inverted pendulum, which has a joint on the foot attached to the ground, and it's just rotating about this joint. There is the linear inverted pendulum, which is just a linearized version of the inverted pendulum. And then you have also the so-called centroidal dynamics model, which is basically just boils down to simplifying your robot, assuming it is just a single rigid body subject to contact forces. And that is a bit more realistic than the linear inverted pendulum, but falls more or less in the same category of simplified models. So what people did in practice is that for bipedal locomotion, especially on flat ground, the linear inverted pendulum works very well, and so people tend to use that. If you want to move to more complex locomotion styles where you're also using your hands, and maybe you're not walking on a flat ground, but you're climbing stairs up and down and doing more fancy stuff, then it would be better to switch to this model, the single rigid body dynamics model, which is a bit more accurate. But the downside is that this is non-linear, whereas this one is linear. So for the rest of today, we're going to focus on this one, which is linear, and it allows us to do trajectory optimization very fast and very simply. So let's introduce how this linear inverted pendulum model works. We can start from the Newton-Euler equation for a single rigid body. So we simply have that mass times acceleration of the robot is equal to the sum of the external forces. So the external forces include also gravity. Gravity, you can think of it as an external force which is applied on the system. And here we have all the other external forces that are coming from contacts with the environment. So this Fi, they're going to be three-dimensional contact forces. You have one of them for each contact point you have between the robot and the environment. So if you're making contact with the environment just with a point foot, then you're going to have just one of these Fi. If you have a square or rectangular foot, then you're going to have one of these for each vertex of your foot. That's the same modeling we used in TSID. So if you have a foot like that, you're going to have 4 contact points, which you can call P1, P2, P3, and P4. And at each of these contact points, you're going to have a contact force which is going to take the name F2, F3, F1, and F4. Something like that. So you're summing up all the contact forces, you're including gravity, and what you get is acceleration of the center of mass of your the body that is in contact with the ground. So this works for a single rigid body, but it also works for a multi-body system like a humanoid. It means the humanoid is still subject to this Newton law, where just C becomes the center of mass of the multi-body system. So it's not a fixed point on the robot, but it's like this virtual point that could even be outside the robot. So if the robot takes a shape like that, well, the center of mass is going to be there, so outside the physical body of the robot. And then we have the equivalent of Newton's equation, but for the rotational movement, which is the Euler equation, which says that the rate of change of the angular momentum, so L is the angular momentum, and it has a dot on top representing the derivative with respect to time, is equal to the summation of the moments applied to the body. And the moments here, since there is no direct moment that is being applied, they're just the result of the contact forces multiplied with the cross product times the lever arm. So the lever arm is the distance between the contact point and the position of the center of mass. That gives you a moment. If you apply a force on a certain point on a body, that creates a moment at a different point, which is equal to the cross product between the lever arm and the contact force. That's mechanics 101. Okay, this is just a definition of all the terms, but I think I've already introduced them all. Okay, so starting from those two equations, so Newton and Euler's equation, if we make a bunch of assumptions, so assume that all the contact points are with a flat ground, so they have a z coordinate which is equal to 0. It could be equal to just any value, but 0 makes it a bit simpler to write down the equations. We assume that we have a constant angular momentum, so L dot is equal to 0, which is quite reasonable during walking. It has been measured also on human beings. We human, as we walk, our angular momentum is roughly always 0. And if you think about it, that's the reason why when you're stepping forward with your left foot, you're also compensating by swinging your arms in the opposite direction. So when you have a part of your body which steps forward on the left, then you also do the opposite with your arms. You need to do it, but when you do it next time you walk, just look at how your legs and your arms move in opposite direction. Well, that is basically your way of making your angular momentum 0. We all do that naturally. Nobody told us to do that, but that's our natural way of walking. And if you take another assumption, which is that your center of mass height remains constant, this is not really true. We have slight oscillation of the center of mass height, but they're sufficiently small that we can neglect them. So under these three assumptions, which are quite reasonable for like standard bipedal walking on flat ground, then you can take the equations from the previous slide, the Newton-Euler equation, and manipulate them a little bit, and you get this expression here. So if you want to see how exactly this manipulation is done, you can take a look at this book chapter, which explains the derivation step by step in a very easy way. So this expression that we get defines the relationship between the center of mass acceleration in the xy direction, so the horizontal plane. The vertical plane is out of the game now because we are assuming a constant height. So the motion in the vertical direction is none by assumption. So we only look now at the evolution of the center of mass in the horizontal plane, so xy. And we can see that we have a quite simple expression that defines the acceleration of the center of mass in terms of the position of the center of mass. And this quantity here on the right-hand side, which is the summation of the vertical forces, Fiz. So we're only looking at the vertical component of the contact forces. And what we are doing is that we are computing basically a weighted average of these vertical forces, or better, we are computing a weighted average of the contact points where the weights are the associated vertical forces. Okay, so here again, I think the drawing I was doing before can help. We have 4 contact points, assuming we have a rectangular foot, which are P1, P2, P3, and P4. At each of these contact points, there's going to be a vertical force, which could be higher or smaller. So F2, F1, F4, F3. And this quantity that we are computing here is just a weighted average between these contact points, where the weights are the contact forces. Contact forces, remember, cannot be negative in the vertical direction because we cannot pull on the ground. We can only push on the ground. So, of course, this quantity here is going to be inside the convex hull of the contact points, because if I'm computing an average with only positive coefficients, and these coefficients are then normalized by the sum of the coefficients. So they're going to be between 0 and 1, because we're taking one particular contact force divided by the sum of all the contact forces. And so the summation of these coefficients is going to be 1. So this quantity here is a quantity that lies inside the convex hull of the contact points, which in this case is just my foot. So depending on which of the vertices of my foot I apply more force, this point is going to move toward that vertex. So if I apply a force only on one vertex, then this quantity is going to be exactly on that vertex. If I apply a force a bit in a more distributed manner, like apply the same force on the 4 vertices, then this quantity is going to be exactly in the middle. And as I apply a force more on one side than the other, this point is going to move towards that side. So physically speaking, this quantity is actually called the center of pressure. Okay, I don't know if you've ever encountered that during your studies, but that's actually one of the possible definitions for the center of pressure when you have contacts between two surfaces. But what we care about is that by definition, this quantity must be inside the convex hull of the contact points, because of the properties that the normal forces can only be positive. So if we make sure that this center of pressure is inside the convex hull of the contact points, then we can be sure that there exist positive normal forces that realize the center of pressure. So basically, we can abstract from finding exactly the normal forces at each contact point. We can just replace this whole quantity with a new variable, z, which represents the center of pressure. And as long as we make sure that z is inside the convex hull of the contact points, then we can be sure that there is a mapping to the normal forces such that all the normal forces are non-negative. Okay, so this allows us to simplify even more this equation, because we get rid of all these normal contact forces, which could be many. If we have many contact points, like a robot with 2 feet on the ground, you have 8 contact points, because you have 4 and 4 for each foot. So you end up with 8 variables, whereas this center of pressure is only bidimensional, because it just lies in the XY plane. So no matter how many contact points you have a constant size of this variable. And you have a very simple constraint for this variable, which is that it must lie within the convex hull of the contact points, which is then a polygon. So if you have just 1 foot on the ground, it's going to be just a rectangle. If you have 2 feet on the ground, like imagine these are your 2 feet, then the convex hull of the contact point is going to be this object here in blue, which is a polygon, but slightly more complex than just a rectangle. Okay, so this expression is the linear inverted pendulum model. And now we can see it basically defines the center of mass acceleration as a linear function of the center of mass position and the center of pressure position. So we have a linear dynamical system here, second order linear dynamical system. This quantity over here is a constant because it's gravity, so 9.81. And this is the height of the center of mass, which we supposed to be fixed, so a constant. And actually, this is the only parameter that depends on the model of my robot. So if I have a higher robot, this equation is going to have a higher value here than if I have a smaller robot. But apart from that, this equation is the same for all the robots. We can also look at the interpretation of this equation, because I think it's quite physically intuitive if you think about it. So basically what this is telling is that the center of mass is accelerated in a direction which is the direction that well, I think a drawing would help in this case. So imagine you have your center of mass here, and instead you have your center of pressure Z there. So this direction, C minus Z, is the following direction. You can imagine it as an arrow that goes from the center of pressure to the center of mass. And this is the direction in which you're accelerating the center of mass. So you can think of this as the center of pressure pushing on the center of mass. I think it makes a lot of sense physically. So like if you have your center of mass here, if I raise my left foot, so my center of pressure is going to be on my right foot, of course, and I get pushed in this direction. Okay. And it also makes a lot of sense that the center of pressure must remain inside the convex hull of my contact point, because of course I can only push on those points. And now we can understand better the limitations we saw before when we were running TSID and asking the robot to follow a center of mass trajectory, which was maybe too high frequency. The robot couldn't do it because basically we have a physical limitation on how much we can accelerate the center of mass, which comes from the fact that the center of pressure can only be inside the convex hull of the contact point. So since we cannot move Z too much to the left or to the right, it must be inside basically your feet. Then there is only so much that you can accelerate the center of mass. Okay. So this equation, I think, is quite beautiful, and it has been the power horse of legged locomotion for probably 20 years. Now people have moved on to more complex models, but until a few years ago, until probably 10 years ago, all walking robots were based on this equation. And well, many still do use this equation even today, because it works just very, very well as long as you're doing bipedal locomotion on a flat ground. Even quadrupedal locomotion can use this. This is not specific for bipeds. This is specific for locomotion on a flat ground. That's the real assumption that we are taking. But people use it actually also for climbing stairs, and with some tiny adjustments, it works as well. The problem is that this is an unstable system. Well, it's not a big problem, but it's just something we need to be aware of. It's unstable because this is pushing away the center of mass. If it was attracting the center of mass, it would be stable. So when you stop controlling the system, the center of mass would go to zero. Whereas in this form, basically, if you stop controlling the system, so you just basically set Z to 0 or to whatever value it is right now, most likely you're going to make the center of mass divergent, so the robot is going to fall down. So this highlights the fact that a bipedal robot or a walking robot in general, it's an unstable system that needs constant high frequency control to avoid divergence. And you could also obtain this equation by taking the dynamics of an inverted pendulum, which is nonlinear, and you could linearize it around the upright position, and you would get the same expression. But I just prefer to derive it from the Newton-Euler equations. Okay, and we can write those linear dynamical equations in the classic linear dynamical system format, where we introduce the variable x representing the state, which contains both the position and the velocity of the center of mass. Your control input is the center of pressure, and you get this linear dynamical system. And typically people represent G over CZ, so the gravity over the height of the center of mass, as W square, because W would be the frequency of the corresponding pendulum. And so, yeah, there is a connection between the frequency of the pendulum and this constant. So this is the dynamics of the system in continuous time. But since for doing trajectory optimization, you need to work with a discrete time system, you can compute the corresponding discrete time dynamics by computing the matrix exponential of this matrix here, which in this case is such a simple matrix that you can compute analytically the matrix exponential, which typically you cannot do in general. And you get this expression here, which contains hyperbolic sines and cosines. I did the derivation once. It's not nice, but it's doable. So this comes from the metric exponential. So this matrix A, and this is AC, A of the continuous system. This is basically E to the delta T AC. That's the relationship between A and AC. That's matrix exponential of that matrix there. And you have a similar relationship between B and BC. It's just a bit more complicated. There is also an integral inside. But this is classic, let's say, linear control theory tools. Okay, so basically when we do trajectory optimization, this is the dynamics that we want to implement. We could have also used a more trivial discretization of this continuous dynamical system using like explicit Euler. But this is really the exact solution of this continuous time dynamics. So it gives you a more precise prediction of the future evolution of the system. An Euler discretization would have looked like x plus equal x plus delta t times x dot, which is ACX plus BCU. This would have been an Euler discretization, which for delta t being very small is going to be very similar to this solution. But if you use a delta t which is large, which is very common when you're doing trajectory optimization, then this solution becomes much more accurate than this solution here. Okay.
You assume U to be constant within the time step.
Yeah, U is going to be piecewise constant for doing this discretization. Otherwise, U would need to be included in the integral that you use for computing B. Good point. Okay, so I think maybe now it's a good time to take a break. Let's take 10 minutes and see you back here at 10:40. Okay, so we have introduced this LIPM, so linear inverted pendulum model. Let's now see how we can do trajectory optimization using this model. So the key idea is to give to the problem a reference trajectory to follow for the center of pressure, which is going to be basically the footstep positions. So we're going to decide in advance where the robot is going to put its footsteps. And we're going to do it that in a very simple way, like, you know, we start here, then we put our foot here, then our foot here, then our foot here, then our foot here, something like that. That's going to be our sequence of footsteps. And we're going to say that ideally, we would like to have the center of pressure to be always in the middle of the foot. So here, these red dots represent the COP, the reference COP. Why in the middle of the foot? Well, because that's a more stable configuration. If the center of pressure goes to the side of the foot, then it means that your foot can tip over on that side. As long as the center of pressure is instead inside, in the interior of the foot, then your foot cannot tip over. So that's the reason why we're asking typically to keep the center of pressure in the middle. We don't need exactly to have it in the middle, but we are just trying to keep it sufficiently close to the middle. And then we're going to have also references potentially for both the center of mass position and velocities. Actually, in practice, people tend not to use the reference on the center of mass position very much. We just use a reference for the velocity. So in this case, of course, the velocity reference should be possibly consistent with the footsteps. So we should ask for a reference velocity that points in this direction, and so that it matches more or less the speed of the footsteps. So maybe we could simply compute the overall distance that the robot has to travel divided by the time of the trajectory optimization problem, and that's going to give us the average velocity of the center of mass, and that is the velocity that we can give as a reference to the problem. So something very simple. So given these references for center of pressure, center of mass, well, the footsteps and the timing need to be predefined, as I just explained. The idea is to keep the center of pressure close to the foot center for robustness. CREF could be a straight line, or we could also not use it. That's what we're going to do in practice. And the problem can be formulated then in this way. So it's an optimization problem where the variables are the trajectory of the center of mass, the trajectory of the center of mass velocity, and the trajectory of the center of pressure, U. And the cost function is simply the summation of the tracking error for these three quantities. And the constraints are the dynamics of the system, initial conditions. If we want, we could have terminal conditions. Those are optional. It depends what we want to do. It is optional. And what we have here are the center of pressure bounds. So these are basically saying that the center of pressure should remain inside the foot. So the foot is this PK, the center of the foot, and S would be the size of the foot. So this is a variable 2D which represents the size in the X and Y direction, assuming you have a rectangular foot. So if this is your foot, then you're gonna have this here is S0 and this is S1. So with this constraint, we make sure that we are not asking for a center of pressure that is outside the foot. You might have noticed that here we are assuming that the robot is on one foot only at each point in time. We never have a double support phase. If we had a double support phase, then we will need to have a more complicated version of this constraint because it's not simply a rectangle, but it's this more complex polygon. But it wouldn't be a problem. I mean, the problem would be the same in terms of form. And by the way, what kind of problem is this? What kind of optimization problem is this? Yeah, but is it convex? Is it linear? Is it quadratic? Is it a semi-definite program?
The lens.
Yeah, it's an LSP. So it's the same kind of problem that we used for TSID. So we can solve it with a QP solver if we wanted to, which makes it even more efficient to compute. So your job is going to be, well, defining the references, these three values here, and tuning these coefficients in the cost, which decide how much weight we give to each of these three terms. But the rest of it is fixed, basically. You don't have to tune anything. So tuning these terms is not difficult, but it's important that you do it right, because if you don't assign the right ratio between the weights, then you might have a diverging trajectory. Well, unless you use the terminal constraint. So if you have a terminal constraint that asks the system to be in a stable configuration at the end, then of course any solution is going to converge to that stable configuration at the end. But if you don't use the terminal constraint, you can still get a stable trajectory that converges to a stable configuration, but you need to tune these weights correctly.
I don't get the point on why we reach this problem. We were asking to decide which is the reference for the center of mass and the center of pressure. And here we are solving for the center of mass and the center of pressure, given a reference that we still haven't found.
Okay, yeah, good point. The key thing to understand is that these references that we are giving, they are not feasible. So this one, you can actually forget about it because in practice, we're not going to use it and we don't need it. So we're only providing a reference for the velocity, but this reference velocity is going to be just a constant value pointing in the direction where we want to move. The robot cannot do that. It cannot move with a constant forward velocity. I mean, you cannot do that either. If you try, it's hard maybe to estimate your own velocity, but trust me, when you walk, you don't have a constant velocity. Your velocity is constantly going up and down, up and down, up and down, because you cannot physically do that. So here we are moving from a rough desired velocity, which is not feasible. And if we gave that to TSID, it wouldn't work, to something that is indeed feasible and consistent with the physical limitations of the robot. So yeah, that's the reason why we need this trajectory optimization problem. So yeah, this C dot ref is not dynamically consistent. It's just a way to communicate in which direction we want the robot to move. So typically, this kind of problem is commanded by a joystick. So you have a human operator which has a joystick in its hand, and it points the joystick in the direction where it wants the robot to move. And the computer reads the command from the joystick. And this command basically becomes the C dot ref. Okay, it's like using a remote control to drive a toy car. And then this C dot ref is used to generate a C dot, which is consistent with the robot model, which is not gonna track exactly that velocity. It's gonna just try to be slightly lower or slightly above, depending on the phase of the walking motion. So on average, it's gonna track it, but not exactly, because that's not physically possible. Okay, so in this first version of the problem that we just saw, we assumed that we were doing the footstep planning, basically. So once we know in which direction we want to move, as I showed you here, we can position some desired footsteps along the path in that direction. Okay, so we want to move in this direction. We decide that the robot can take steps that are, I don't know, 50 centimeters at most. And so we position the footsteps 50 centimeters apart from each other, one on the right, one on the left, one on the right, one on the left. Okay, and we do that manually. It would be better to figure out a way to make this optimization problem automatically compute the footsteps, so we don't have to do it on our own. And actually, it's pretty simple to do it. We're gonna do it, but we're gonna maintain the footstep timing fixed. So the duration in time of the footsteps is gonna remain fixed, just to clarify. The way we do this is by adding the footstep position as an extra decision variable in the problem formulation. We're gonna call it P. And we can do it by maintaining the problem as a quadratic program. So well, an LSP to be more precise. And this has been proposed in this paper in 2010. The idea is that since now the solver is able to move the footstep position wherever it wants, we need to tell it that actually two successive footsteps cannot be too far apart from each other, because the robot has a finite size leg. So if your first footstep is here, your second footstep cannot be 5 meters in that direction. So it must be close to this one. So we need to bound the distance between successive footsteps. And this is a modified version of the problem where the modifications are highlighted in red. So now we have the extra variable P, which is a trajectory of footsteps. This P then becomes also the reference for the center of pressure. And it becomes also here part of the constraints on the center of pressure bounds. But this was also there before. So the only extra constraint that we need to add is this one, that the position of the footsteps at time k and k+1 must be bounded inside some polygon. The shape of this polygon is going to depend on the kinematic limits of your robot. So if your robot has longer legs and can take longer steps, then this polygon is going to be larger. If your robot is tiny and it has tiny legs, then this polygon is going to be very small. And you need somehow to define a polygon that approximates the kinematic limits of your robot. So this is the only really extra work that you need to do for making this footstep planning automatic. But apart from that, the problem remains basically the same. So now we only have to provide basically the reference velocity, because as I told you, this term here is not needed. And now the last term doesn't require a reference from you. So you're only providing a reference direction for the velocity and a magnitude, and then everything else is planned automatically for you by the solver, which is quite nice. Any question on that? Okay. Okay, how do we implement that in Python? So I'm gonna highlight here some parts of the script and I'm gonna show you and run together. So of course you need to know some parameters of your robot in order to make this footstep and COM trajectory planning. Two very important parameters are the foot length and the foot width, because those are basically the bounds for your center of pressure. So we get the foot length by taking the negative foot length plus the positive foot length from the same configuration file we used in TSID. Then we need to decide how many time steps we have for each footstep. We need to be careful now when talking about steps, because it could be a time step, so dt, or it could be a footstep. So we have same name for two different quantities. So I'm gonna try always to say either footstep or time step, never just step, because that's ambiguous. So here we take the duration in time of a footstep, and we divide it by the time step delta t. And that gives us the number of time steps per one footstep. And then the total number of time steps of my trajectory optimization problem is going to be the number of steps times the number of time step per footstep. Okay, I'm just computing how long my horizon is going to be, basically, starting from the duration of one footstep and how many footsteps I want the robot to take. Then I need to initialize the center of mass state. And I'm going to assume that the center of mass starts exactly on top of the first footstep. So the robot is starting with the center of mass on top of one foot, so that it can immediately take a step with the other foot. I cannot start with the center of mass in the middle of the 2 feet, because otherwise, if the robot raises 1 foot to take a step, it's going to fall down on that side. So the robot starts already with all its center of mass on 1 foot. So even if the other foot is lifted, it's still in static equilibrium. And for the velocity, I'm going to assume it starts with 0 velocity. Then at first, we're going to do an implementation where the footsteps are manually placed. So I've already written down a simple function called manual foot placement, which takes the position of the first footstep, the length of each footstep, and the number of footsteps that we want to take. And it computes as the sequence of footsteps. And I run here this function for a specific case, just to show you. In X, basically, the first footstep remains at the same at the same value, and then you have just a linear forward movement in the X direction. And for Y instead, since we are switching from left to right at each footstep, we have this zigzag trajectory. Once we have the footsteps trajectory, we need the corresponding COP reference trajectory, if you use the formulation where this is provided. So here we're going to use this function, create COP trajectory, which takes the reference footsteps and it computes the corresponding COP trajectory, which is just tracking the footsteps. And so if we execute it with the previous input, what we get is this COP trajectory, which is just tracking the previous footsteps trajectories. So you can see it more clearly now what happens. This is basically the duration of the first footstep. So we can see that the reference COP is remains constant. And then when we move to the next footstep, we switch value. So, and we have again two constant values, and we keep having piecewise constant values here and here and here. So this would be 1, 2, 3, 4 footsteps. Is it clear? Okay, so now we can move to the code. Probably it's a good idea for you to update your ARC repository, because I'm constantly working on this and pushing small changes. There is a folder called LIPM, and we can open this file called LIPM_OCP to see how I implemented this trajectory optimization problem. So let me close this. And let me open LIPM OCP. So we can start by looking at the main function. So in the top part of the file, you have a class LIPM OCP, which we're going to look at later. And then in the bottom part, you have the main function, which is where the execution of the file begins. So here, more or less, the first part of the main is what we have already seen in the slides. So we define all these parameters. We compute the manual foot placement. We compute the reference COP trajectory corresponding to the footsteps. Then we compute a reference also for the center of mass position and velocities. So the one for the center of mass position is not going to be used. So we just set it to 0 because in any case, we don't use it. And for the center of mass velocity, it's just going to be a constant value, which is equal to the length of a footstep in meters divided by the duration in time of one footstep. So that gives us basically the average velocity we expect the robot to have. And we just apply this constant reference for the velocity. And then we create an object of this class LIPM OCP, to which we give some hyperparameters, such as the time step duration, the number of time steps, and the height of the center of mass, which is defined in the configuration file. And then we call this solve method twice, one for computing the reference in the X direction, and one for computing the reference in the Y direction. So this is not how I showed you the problem in the slides. So in the slides, everything was coupled, X and Y. But in practice now, since we are moving in a straight line, the footsteps are rectangular and we never turn them. Basically, the X direction and the Y direction are completely decoupled. So we could solve it as a unique problem, but we can solve it also as two independent problems, one for X and one for Y. And this is faster, of course. If you can decouple a problem with 1,000 variables into two problems of 500, that's much faster. That's about 4 times faster, because the complexity is cubic. So every time you double the number of variables, you multiply times 8 the computation time. So it's better to have 2 smaller problems than 1 bigger problem. So when we call the solve function, we need to specify the initial state of the center of mass, x0. Then we have these three parameters, WC, WDC, WU, which are the weights of the three components of the cost function. So the reference tracking error for the center of mass position, velocity, and center of pressure. So these parameters are defined in the configuration file, which we can open in a moment. Then we specify the references for C, DC, and U. And finally, we specify the bounds on the center of pressure, which are, in this case, the foot length divided by 2 for the X direction, and instead the foot width divided by 2 for the Y direction. And then we just have plots and saving the data. So we can now move to the class LIPM OCP, which is defined above. So we can see that in the constructor, we do almost nothing except for computing omega. Omega is that constant that we already introduced when introducing the LIPM dynamics, which is the square root of the gravity divided by the height of the center of mass. So this is going to be used for computing the LIPM dynamics. And then in the solve method, we use the Casadi library, which is a library for doing optimal control and numerical optimization to define an optimization problem. So first, we create the variables of the problem, which are the state trajectory and the control trajectory. So the state trajectory is a trajectory with n plus 1 variables, each variable of size 2. So it's basically a matrix of like 2 times n plus 1. The control is the COP, which is a scalar. And so we just have n variables. Here I'm just renaming this self.x, self.u, self.w as x, u, and w, just to have shorter names in the following. Then I'm defining the cost function. The cost is initialized with zeros. And then I'm just summing up the running costs, which are nothing more than the weight. So for instance, WC times the tracking error for the center of mass position and the center of mass velocity. Also the center of pressure if the time step is not the last one. At the very last time step, we don't have the center of pressure defined because in trajectory optimization, the control inputs stop at time step n-1. They don't have we don't have control inputs for the last time step because they would be useless since we are not computing the state afterwards. So we are summing up all this running cost for all the time steps, and that's the cost that we pass to the solver to minimize. So we want to minimize this cost. Then we need to define the dynamics of the system. So actually this part here was just an experiment, so you can comment it. We define the hyperbolic, cosine, and sine, which are part of the dynamics as we introduced it before. And we introduce the dynamics as constraint into the problem. So we compute the next center of mass position as a function of the current state of the center of mass and the current center of pressure. And we do the same for the center of mass velocity in the second line. We also define the bounds on the center of pressure, U, which is just uref minus umax or uref plus umax. Lower bound and upper bound for the center of pressure. We define the initial condition as a constraint, so x0 must be equal to x init. And then if we wanted to, we could have terminal constraint, but let's just comment these 2 lines right now, and then we discuss them later. Finally, we simply call the solver, which is IPOpt. In this case, that's the default option for Casadi to solve the problem, and we return the solution. Okay, so let me go in that folder. GD LIPM, Python 3, LIPM, OCP. Correct. I'm not in the right virtual machine. Sorry about that. So I need to run the other Docker image, which is not latest, but Casadi. Okay. Now it should work. Okay. So we can see here in the plots the planned trajectories. So this is for the x direction of the center of mass. And here we are seeing the given footsteps, which are this piecewise constant function here. We can see that the center of pressure, which is the green line, is basically tracking perfectly the footstep, which means that the center of pressure is always very close to the center of the footstep position, which is what we were asking for. And instead, the center of mass is this blue line here, which we can see it's roughly following the footsteps, which makes sense. We don't want the center of mass to be too far from the footsteps, otherwise also kinematically that wouldn't be feasible. And we can see here the center of mass velocity, which, as I told you before, cannot be a constant value. So even if we are tracking a constant reference velocity, the velocity that we get for the center of mass is not at all constant, and it has this typical shape with these spikes. Okay. So of course, the point of these spikes corresponds to the moment where we moved from one footstep to the next one. Because when we do that, basically our center of pressure jumps from one foot to the next, and that creates a discontinuity in the acceleration, which we can see because here the velocity is non-differentiable. So you see, connecting to what we were discussing before, even if the center of mass trajectory is not differentiable because the velocity has this point of non-differentiability, the problem that we have is completely differentiable. It's just a QP. Okay. So this is the x direction, and this instead is the y direction. So this is quite different because in y, basically, the reference velocity is 0. On average, we are not moving, we are just oscillating left and right in the lateral direction. So these are the footsteps, which go from minus 0.1 to 0.1 back and forth. So we have like this square wave function. The center of mass is also oscillating between the 2 feet, moving left and right. And the center of mass velocity, it also has these spikes, but they're not always in the same direction. Here they are moving to a positive velocity, and here they are with a negative velocity. And we oscillate left and right, left and right. Okay. Here you can notice that the last state of the system is not really ideal because we are ending with a non-zero velocity. So this could possibly be problematic if we want to track this, because I mean, this is feasible, but then there is nothing ensuring that at the end we can then stabilize the robot. So maybe, yeah, we take these 1, 2, 3, 4, 5, 6 steps, but then at the end, the robot is in a state where we cannot stabilize it and it's gonna fall down. So to avoid that problem, we could introduce a terminal constraint. So if we go here, a first thing that we could ask is simply to have the terminal velocity to be 0. That would be already a good starting point. So we can try just to add this constraint and see what we get. So this is in the x direction. We can see that the velocity at the end now is going to 0. Here we end with a 0 velocity. And the center of mass ends in a position which is also very close to the last footstep. So it's almost on top of the last footstep, which is good. So it means that we can stabilize it. And in the y direction, yeah, we end with a 0 velocity. And we can take a look also at the center of mass position. Also in this case, we are quite close to the last footstep, not exactly there. So here we are at 0.93, whereas this would be 0.96. So we are 3 centimeters off in the lateral direction with respect to the middle of the footstep. So if we wanted to be exactly on top of the middle of the footstep at the end, which would be good for making sure we are in a stable configuration, we could add also this terminal constraint here, which says that the center of mass position at time step n, so the last one, is equal to the reference COP position for time step n minus 1. We don't have a reference COP for time step n, so we need to take it at time step n minus 1, but well, the COP, the footstep is going to remain there at time step n or n minus 1, doesn't change anything. So we can enable also this constraint and rerun, and now we should have an exact match of the terminal COM. Yeah. So we can see now the terminal COM position is exactly on top of the footstep. This is X, and this is Y. You can see it's exactly there. So this is a perfect trajectory, I would say, to try to track with TSID later. We can take a look at also at the hyperparameters, which are defined here in this file Romeo conf. I think, let me see something interesting. Yeah, okay, so here we have the 3 parameters for the cost function of the trajectory optimization problem, the 3 weights. So we are using a weight of 10 for the COP tracking and a weight of 10 to the minus 1 for the tracking of the velocity. So one thing we could try is to make these 2 weights equal and see what would happen. And maybe to make this more clear, we could also add the plot of the reference velocity. When we're, of course, plotting the x direction, because in the y direction, the reference velocity is just 0. Okay, let's see if this works. Well, maybe we can plot this first using the previous weight. Okay, so this green line is the reference velocity, and we can see that the real velocity oscillates above and below it, as I predicted. So now we can change this weight. Instead of 10 to the minus 1, we simply set 10. And we can try to run this again and see what changes. Okay, you can see now we have a velocity of the center of mass, which is much closer to the reference we are giving. So the spikes are much smaller, which is reasonable because that's what we asked. But the downside of this is that now our COP is not tracking well the footstep configuration. So we can see the COP is this red line. And now the COP is very close to the COM. If you think about it, it makes sense. If you want to maintain your velocity constant, it means that your acceleration must be 0. And the LIPM model says that the acceleration is proportional to the difference between center of pressure and center of mass. So if you want your acceleration to be almost 0, your center of pressure should be very close to your center of mass. And this is what is happening here. Do you think this is good? No. No, it's not good. It's not good because we want the center of pressure to remain close to the middle of the foot. We don't want it to go too close to the boundaries of the foot. Otherwise, it's dangerous because the foot could tip over in practice. I mean, in simulation, probably it's going to work nonetheless, but it's not a good idea for robustness than on a physical machine. So that's why typically you assign a higher weight to the center of pressure tracking than to the center of mass tracking, because the center of mass tracking is something you don't care too much about. You only care about getting there in the end. So actually, since we introduced the terminal constraint, we could even say that we don't care at all about tracking the center of mass velocity. And we could try to see what happens. We could set the weight on the center of mass tracking to 0. Unless there are numerical issues, I think in theory this should work. Yeah. And actually what we get here is very similar to what we were getting before. So this shows that actually the only cost term which is really playing a key role here is the minimization of the center of pressure tracking. The rest is not very important. This is because we have introduced the terminal conditions, of course. If now I remove the terminal conditions, I need to reintroduce the penalty on the center of mass velocity. Otherwise it's just going to be unstable. We can give it a try just to make sure that everything makes sense, but I think it's pretty reasonable. If now I remove these two and I rerun it, it's just gonna go unstable. Yeah. So it does something kind of reasonable until the very end. Probably because I don't know why. Probably there is some regularization inside the solver. That's a reasonable explanation. So the solver is adding some regularization to the variables, trying to maintain them close to 0. And so if it went unstable from the beginning, the COM position and velocity would take very large values, which the regularization is preventing. But at the end, the regularization of the solver is not enough because it's probably too small. And so at the end, we do have a divergence. So we can see that the center of mass is diverging in the negative direction. And this is not something that we could stabilize on the real system. So basically, we could either have the penalty on the velocity, or we could have the terminal conditions. One of them is sufficient to get a reasonable trajectory to work with. Okay. So we can now go back to the slides to start discussing, once we have a reference trajectory for the COM, how do we connect this trajectory to task space inverse dynamics to make this run on the complete model of the robots? So we have two issues which we haven't addressed so far. One is the time steps. So when we are doing trajectory optimization with LIPM, we are using a quite large time step. I probably didn't show you, but it's 0.1. So it's 100 milliseconds. So that's not a time step we can use in task space inverse dynamics. In task space inverse dynamics, we can go at most to 10 milliseconds, but 5 would be better. So we need to interpolate the trajectory that we get from trajectory optimization to something which has the same time step of task space inverse dynamics. Otherwise, the two things don't match. And the second missing piece is the trajectories for the feet. Because with LIPM, we simply say where the footsteps are at each point in time, but we don't say how the feet are actually moving from one footstep to the next footstep. So we need that additional piece of information because task space inverse dynamics is going to need that for tracking the footsteps. So let's talk about interpolation first. How do we interpolate? Well, we have a center of mass position and velocity trajectory, and we have a center of pressure trajectory with a large time step. And what we would like to compute as an output is a center of mass trajectory, including position, velocity, and acceleration, with small time steps. And here we have different options. We could do a linear interpolation, but that wouldn't be very accurate. A better option is to do the interpolation using the LIPM dynamics, which we have already computed, because that gives us the exact interpolation between two pointing times. So we simply use here as dt the time step of TSID, so a few milliseconds. And we plug in here the computed COP value. We plug in here the value of the center of mass at one point in time, and we compute then all the intermediate values by computing this expression in a loop a few times. Since we also need the acceleration in TSID, we can also compute the acceleration using the LIPM dynamics, which gives us acceleration as a function of the position and the velocity, because using the discrete time dynamics, acceleration is not computed automatically. We just compute position and velocities. The acceleration is bypassed. Next thing, the trajectories for the feet. How do we compute them? Well, here we have an infinitely many options. A very common choice is to use polynomials because they are very simple to work with. So what we want to make sure is that the trajectories that we compute match the initial position of the footstep, the initial velocity, which is 0 because the foot needs to start with a 0 velocity, the final position of the footstep, and the final velocity, which needs to be 0 as well. Otherwise, we're going to hit the ground, and that's not something we want to do. So since we have 1, 2, 3, 4 constraints, we need our trajectories to be at least third-order polynomials. Because a third-order polynomial is going to have 4 parameters, and I need at least 4 parameters if I want to satisfy 4 constraints. If we want to add more constraints, such as 0 acceleration at the beginning and at the end of the motion, of course, I need to increase the degree of the polynomials. Otherwise, I cannot solve the system. So we can take a look at how these things are done in the following script, which is called LIPM to TSID. Maybe before we do that, let me clarify a bit how we do this polynomial trajectory generation. So let's suppose we are using a third-order polynomial. So it's going to be something like a plus b t plus c t squared plus d t cubed. That's going to be the position of my foot at time t. So it's a parameter with respect to time. And then basically I can write down a system of equation where I say that p of 0 is going to be equal to my initial footstep. So let's call it S0. The position at the end, so at time t, must be equal to my footstep, my next footstep, S1. And then I need also to say that p dot of 0 is equal to 0 because I start with a 0 velocity and I want to end with a 0 velocity. And p dot is very simple to compute. I simply need to compute the derivative of that polynomial, which is going to be the following one. Okay, so both the polynomial and the derivative of the polynomial are linear functions of the parameters. So the parameters are A, B, C, and D. So we can see that they appear linearly. So this system of equations here is just a linear system. So we can compute the solution just by inverting a matrix. It's going to be a square linear system because we have 4 equations and we have 4 parameters. Okay, that's why we needed at least a third-order polynomial. Because if you use a polynomial with a lower order, then we have less than 4 parameters, and the system of equation in general is not going to have a solution. Okay. So what I just wrote down here works well for computing the reference in X and Y, so the horizontal plane. For the Z, it's a bit different because in Z, we start at 0 height and we finish at 0 height. So if we simply say we want to start at 0 and finish at 0, well, the polynomial is going to remain at 0 all the time. So that doesn't work. So for that, we need to do something that is slightly more complicated, and we have different options for doing it. So in that, what we want to do is you want to reach a certain height in the middle of the footstep, and then you want to go from that height back to 0 in the second half of the footstep. So you could either compute this as two trajectories, one going from 0 to a certain height in half the footstep duration, and the second one going from that height to 0 in the second half of the footstep duration. That is one option. And in that case, you can use the same formulation as here, because you have the same constraints. You start at a certain position, you finish at a certain position, and you start and finish with 0 velocity. So you can use third order polynomials, is that they're just going to be 2 instead of 1. Or another option would be to use a single polynomial for representing the whole trajectory, but you need to introduce an extra constraint, which is that in the middle, so at time t divided by 2, you need to be at a certain value, at a certain height. And if you do that, however, you can no longer use a third order polynomial because you have 5 constraints. And so you need to switch to a polynomial of a higher degree. So the solution that I've used in the code is the first one, so that I can always work with polynomial of order 3. So it's easier, I can reuse the same code twice. I'm just going to generate 2 polynomials for the z coordinate instead of 1. Okay. So we can take a look at the code. So in the same folder, you can find LIPM to TSID. Let's start looking at the main. Here's just commented stuff, which we can delete. So the script starts by reading the trajectories that have been generated by the previous script, the one solving the trajectory optimization problem, and getting the trajectory for the center of mass and the center of pressure sampled with the time step of the OCP, so 100 milliseconds. And then we do first the interpolation of the center of mass trajectory, calling this function interpolate LIPM traj. And then we do the computation of the footsteps using these functions, compute foot traj twice. We do it twice because we do it once for the right foot and one for the left foot. And then at the end, we save everything in a file, which is going to be read by yet another script, which is the one running TSID. And then we are just doing some plots. So we can now take a look at the functions above. This is a simple function evaluating the dynamics of the LIPM in discrete time. So it's just an implementation of the expression we saw in the slide with the hyperbolic sines and cosines. And then we have this interpolate LIPM trajectory, which does a for loop. And at each iteration of the for loop, it initializes the COM position and velocity with the one computed by trajectory optimization. And then it does interpolation with another for loop where it calls the discrete LIPM dynamics function we saw a moment ago to compute the next state of the COM, and it adds that to the interpolated trajectory. And then above, instead, we have the function for computing the foot trajectory. So what we do here is simply calling this function compute third order polytraj, which takes the footstep position, the current one, the one of the next step, and it computes a trajectory that is interpolating between the current footstep and the next footstep. So actually that is what we do for the directions X and Y. For the direction Z instead, what we are doing is that we start always from 0. We reach the desired step height using half of the time of this time of a footstep. And then for the second half, we start with the desired step height and we reach 0 using again half of the step time. So exactly what I described a moment ago. So if we run this script, Python 3, LIPM to TSID, we can see the generated trajectories. So this is the reference for the footsteps in the direction X. So we can see the first step that we take is half the length of the others because the feet start aligned. So to make things symmetric, the first footstep needs to be half the length of the other so that afterward everything is always aligned. Well, these are the footsteps in the Y direction. Since I'm not moving laterally, each foot remains always in the same Y coordinate. And these instead are the feet trajectories in the Z direction. So we can see they always start from 0. They move up to a certain height, which is 5 centimeters in this case, and then they come back down. And here now we have the interpolation of the last trajectory, which we executed, which was the unstable one. So of course I should rerun the first script before running this so that I get the interpolation of the correct trajectory, not of this one. But we can see that the trajectory is good. I mean, it's well interpolated. That was the X direction, and this is the Y direction. See? Okay. Okay, so let me rerun the first scripts, otherwise I don't have the correct data then later to move on. Okay, so now we have a good trajectory for the LIPM, and now I can rerun this. So the trajectories for the feet, of course, are the same, but now the one for the center of mass, we can see that it's a good one that finishes exactly on top of the final footstep with a 0 velocity. Actually, here we have, I didn't notice, we have 2 trajectories which are superimposed. We have the one computed with TO and the one interpolated. And if you zoom in, you're able to see the difference. You can see that the one computed with trajectory optimization is this one's with a dotted line. And we can see that it's a piecewise linear function because when we're plotting, the matplotlib is interpolating with a piecewise linear. And instead, the one that is interpolated by us is not a linear interpolation, but we can see that there is a curvature due to the fact that we are using the LIPM dynamics. Okay, and this is the one for the Y direction. Looks good. Okay. So the final step would be now to take these reference trajectories for the center of mass and for the feet, import them inside a script which uses TSID to track these reference trajectories with the full body model of the robot so that we can see the robot walking inside the viewer. But since we have only 5 minutes left, I would stop here for today and we can do the final step on Friday. Giulia, sei ancora lì? No, se n'è andata. L'ho beccata, sapevo.
Sì, scusa, in questo momento la connessione non è proprio ottima.
Ok, se vuoi io sto anche registrando, se ti servono le registrazioni fammi sapere. La connessione mi sa che è pessima. Vabbè, poi mi farai sapere in qualche
Sì,
modo.
è proprio questi ultimi... Va bene, grazie mille.
Ci vediamo venerdì.